Okay, I want to just do a few solutions here. Number 13 from 240, we've got h of x is equal to the square root of x squared plus 1, and we want to find out the first and second derivatives. And the main thing is algebra here. Now this is, let's rewrite this as x squared plus 1 to the 1/2. So the derivative is going to be 1/2 times all that to the minus 1/2 times the chain rule. And so that's going to simplify as x, and then I'm going to rewrite that with a quotient, because when you've got a product of positive powers times negative powers, it's tempting to use the product rule, and you can get the correct answer, but it's often better to use the quotient rule, because the quotient rule sort of automatically tells you to do an important algebra step in the process, namely to put things over a common denominator. So now we want to take the derivative of this expression, h prime, and that's going to be the quotient rule. So derivative of the top, let me make it a quotient. Derivative of the top is 1 times the bottom left alone minus the top left alone times the derivative of the bottom. Now it happens to be, hey, the derivative of the bottom, that's x squared plus 1 square root. Oh, that's exactly what I know the derivative of. Well, so that's handy. I can just plug that in there. Now you don't have to observe that, but that's what you're going to get. That's going to be the derivative of h again, because that h was a part of h prime. Then all divided by the bottom squared. Well, that's kind of nice. The square root then squares out. Okay, now you might think, oh, I'm done. It's a mess, but big deal. Okay, but this is the kind of expression you absolutely have to simplify. When I've got a compound fraction, I've got stuff involving fractions in the middle of a bigger fraction, you have to simplify that. It's not optional, and very often it will simplify pretty significantly. This one simplifies dramatically. So what do we need to do? Well, this guy needs to be over a common denominator. So let me just copy that. Okay, so this part here is over 1. So I'm going to put it over square root of x squared plus 1. So let's just, so I don't need the 1 in front of it. So if that's going to be over the square root of x squared plus 1, then the whole thing is not going to be square, the top is not going to be square rooted anymore. So I just multiplied by the square root of x squared plus 1 over itself, and that's what I'm getting on the top. Let me make this a little bigger. Hey, that's better, isn't it? Okay. So now I can put them over a common denominator. Let's copy it down. And so that's going to be x squared plus 1 minus x times x. Minus x squared. So that takes care of all that. Okay, so now just to make sure it's clear, that's all in the top. And then we can see a simplification, and this is the key to why it looks rather pretty at the end of the whole thing. The x squareds cancel. A little bit surprising, but that's how derivatives work sometimes. You get nice stuff. And so now I've just got to figure out that compound fraction. The way most people like to do it is they express the bottom. Let me go ahead and make that into a fraction, but with a 1 denominator. And then it's going to be this numerator times the denominator flipped. Oops. There we go. And so it's just 1 on top, and then it's a half power of x squared plus 1 and another power, so rules of exponents tell us that it's x squared plus 1 to the 3/2. So turns out this is a really important calculation. A version of this calculation is the key to why gravity works, for example. It's really not a random example at all. It seems very finicky and weird, but it's very, very nice that this works out in such a pretty way. Oops, sorry, getting distracting. Okay, so now let's look at 17. H of t is tan 3t, and h prime of t equals, I gotta check my time real quick. Okay. Okay, so that's going to be, let's see, the derivative of tan is secant squared. And I'm going to make sure, I'm going to put parentheses in here to make it really clear that that's a function inside of a function. So we've got the derivative of the outer, but then the derivative of 3t gives you a times 3. And we'll just clean that up a little bit by putting the 3 in front. And now h double prime of t is just the derivative of that. Well, the 3 is still there. Now, oh my goodness, nobody told me that this was going to give me a 3-stage chain rule. This is one reason, you know, we do 3-stage chain rules. This was just a regular 2-stage chain rule, but now with the second derivative, oh man, I got to deal with the derivative of something squared. Okay, so the 3's there. The derivative of something squared is 2 times that something, little dot, and I just write what that something was without thinking about it, but then times, and then the derivative of everything but the 3 and the square, the secant 3t. Oh, okay. Now that's a little tricky because I'm going to put it in brackets. That's secant of what's inside times tangent of what's inside. This is a little bit of a weird thing that most of the time we're not used to having to write the x or the 3t or whatever's inside twice. But the derivative of secant is the secant times the tangent of the same thing. And I'm still not done because that's just the derivative of the secant level. I still have to strip that off and say, aha, times the derivative of 3t, which is 3. And so that's going to be 2 times 3 times 3 is 18. There's 2 secants. At least one person was asking me, why do you get secant twice? Well, one is from the fact that it's derivative of something squared. The other is from the derivative of secant, has a secant in it, but it's actually secant tangent. And then tan 3t. Okay, next one is 23. There, we want a third derivative. Y equals square root of 2x plus 3. And I'm going to go ahead and rewrite that as 2x plus 3 to the 1/2, because that's how often people like to do it. Y prime, okay, so it's something to the 1/2, so that's 1/2 times that very thing to the minus 1/2 times 2, because the derivative of 2x plus 3 is 2. And that simplifies nicely. That's 2x plus 3, oops, to the minus 1/2. So now let's go to the second derivative. That's the derivative of something to the minus 1/2. So that's minus 1/2, 2x plus 3. That thing, take it down another notch, minus 3/2, and then times 2. Just because it's the second derivative doesn't mean the chain rule is not enforced. All we're doing is we're starting over. This function y prime, and we're taking the derivative of it. The chain rule still happens. The halves still happen to cancel out, which is kind of nice. And now, third derivative, same deal. So the minus is still there in front. Then this minus 3/2 comes down, so it's going to be plus 3/2, 2x plus 3 to the minus 5/2 times 2, once again. And so that's going to be 3 times 2x plus 3 to the minus 5/2. And the last one was 43. Let me check time.